So you want to turn it on back there, Denny?
Might work better if you're not light.
Yeah. Okay.
We're going to go for the little camera.
Okay. I think if I had these adjusted right there, this would be out of the way for most of the time. Now what we want to do now is show you some slides that would illustrate some of the types of circuit breakers and some of the principles that we've been talking about. So you want to get the lights there, Ken? Yeah, let's see, how's the focus on that? Does that look pretty good?
Very good. Yeah.
Now this is a 69 kV type G04B circuit breaker. As you can see, it has many of the same things that we previously talked about. It's a 3-tank breaker. 3 tanks there. There's the porcelain bushings there. The operating compartment at this end. This is the mechanism for translating the operating mod motion from vertical to horizontal, running along back through there. And then this projection right here houses the tripping spring that we mentioned previously. Some of the other things here are the framework for the breaker, the operating compartment. I guess that probably covers most everything. We may come back to this later. This is a view of the operating mechanism of this type of circuit breaker, and which this cylinder right here houses the solenoid that's used to open or close this circuit breaker. Just pull this rod here up or down. And the rest of the mechanism here is some of the controls for this solenoid. We'll get into that at a later session of this class. These terminal boards here house the leads for the current transformers that are mounted on the 69 kV bushings. They come from these conduit here attached to these terminals here. Then depending upon the particular connection that you would desire for the circuit breaker, then you can make your connections to these terminals right along there. Another type of 69 kV 3-tank circuit breaker. This I think is an Alice Chalmers. This particular view here doesn't house too much. It's different from the G04B. It's included here because it has a different type of an operating mechanism. This happens to be a compressed air operated mechanism. This is the air storage tank up here, the air compressor motor, some of the controls here for the pneumatic air piping. And this shows some of the control wiring for the circuit breaker. Here's another view of that same circuit breaker. There's the air compressor motor up there. Now this is a 69 kV single tank circuit breaker in which we have the 3 phases in the single tank. There's the operating rod here, and everything's much more compact. It's much smaller than the 3-tank breaker. This is a view of the operating mechanism for this particular type of circuit breaker, showing the heavy springs and the gear motor here that are used to compress these closing springs, and then they're finally released to close the breaker. It's another view of the other side of this operating mechanism. There again showing some of the cams there that show why this is a mechanical engineer's pride and joy. It's another type of single tank breaker. You can see a little different housing. It's a bigger diameter housing. It hasn't been installed yet, but this particular circuit breaker has a hydraulic operating mechanism that we just showed in one slide briefly. Here's the tank in which you have two different pressures of fluid, one a more or less atmospheric pressure, and then inside of that you have a higher operating pressure around 3,000 psi, which is stored in this accumulator right there. And then it's directed by appropriate pilot valves and solenoid valves through the proper channel to finally end up pushing or pulling, and actually it's just pulling this operating rod here. And in this circuit breaker we can see the current transformer leads going out to the breaker, the control switch at the breaker, and some of the, well, here's the compressor for the hydraulic fluid there. Now, the next group of breakers are some 161 kV breakers that we don't have as much detail, and we'll go through them fairly rapidly because we may want to come back to them at a later date during our discussion of breaker installation. This is just a view of the type of foundation used for 161 kV circuit breaker. This is the 3-tank 161 kV circuit breaker. The porcelain bushing, there again you notice the tremendous difference in size. It's being loaded on this multi-wheel dolly to be moved from the railroad car to its foundation. And this shows the railroad car that it was shipped on, and then it was moved over there. All 3 tanks are mounted on 2 steel I-beams. Showing how it's going to be rolled onto the foundation. One of the things in any kind of breaker installation is protecting the porcelain, which they're trying to do there. And this shows it being installed on a pad with isolating disconnect switches on either side. This is another breaker being unloaded. In this case, the whole thing is picked up by a crane instead of being skidded on the car. Yeah, I think I got it. Yeah, that other guy. Now we have a few slides of 345 kV circuit breakers, showing them coming in on the railroad car. These tanks at the, well, I guess we have some better views of that later on. They're being unloaded here, in which you have the operating tank here for air pressure, the porcelain columns here, and the top here are the interrupter heads that we previously described. I don't think I have a picture of those too well. We'll have to get one later. Being picked up to be placed on their own foundation. I guess that'll be all the slides for the time being. That gives may give you a little better idea of some of the actual circuit breakers that we're using. Circuit breakers are really kind of something that developed out of a particular need in the industry. In the early days of the electric industry, people hadn't the slightest idea what circuit breakers were, what generators were, what they were doing. So as a result, they had a lot of unusual circumstances happen. And on some of the earlier generating stations, as pre-1900, they basically ended up by putting out a arc, opening up a circuit by shutting down an entire plant. The next step after this plant shutdown type of circuit breaker is what they call a fused air circuit breaker, which is basically nothing more than a air switch, a disconnecting switch with a fuse wire connected to one end. So every time they opened up the disconnect switch, they fused the fuse and interrupted the arc. This wasn't the complete answer, because the fuses themselves were nothing more than a little piece of wire which, as the generating stations grew larger in capacity, couldn't interrupt the arc either. So they had quite a few complete system shutdowns and interruptions before they got anywhere near developing a circuit breaker. One of the big questions in the early days of electricity is whether they should build substations inside or outside. And the first outdoor circuit breakers were developed in 1909. And these were the oil-type circuit breakers, and they had many of the same ideas that we have now, but the technology of that age just wasn't far enough advanced to give a circuit breaker with much assurance of putting out an arc when it tried to operate. 1920s short circuit testing, one of the major developments that allowed a manufacturer to test a circuit breaker and guarantee that it would meet some interrupting requirements. And since then we've developed ASA standards that are listed in as references on your notes there. These give certain standard ranges of voltages and currents in interrupting rating. Which we'll get into a little bit later on the selection. The present state of the art of circuit breakers, each manufacturer must meet certain design tests before he can advertise this particular breaker as completely ready for sale. These are tests that test the continuous current rating of the circuit breaker, as it must carry a certain amount of amperage without exceeding a definite temperature rise. It has a short circuit test where you have to interrupt a fault of a given magnitude. It has a dielectric test similar to that for transformers, where you have to withstand certain impulse voltages. It must switch the load of the given circuit, that is the full load rating of the continuous rating of the circuit breaker. It must switch that as a load. And finally it's tested as far as mechanical life to make sure it'll meet a certain amount of mechanical life requirements. In writing our circuit breaker specifications, basically we start off with the voltage rating. This is a design voltage, and built into the specification is the maximum voltage that this circuit breaker can operate on and meet all its current requirements. The current rating is the normal continuous rating that this breaker will carry all the time. And just to get around having numerous sizes of circuit breakers, they have standardized the current ratings into several values. Current ratings that are standard start out about 600 amps, 1200, 1600, 2000, and 3000 amps. Now you can get higher ratings than this, but there again they're special to manufacture. The insulation levels and BILs are the same values as previously discussed on transformers, so that you can get a coordinated installation between a circuit breaker or a transformer. Interrupting capacity is a value that is the three-phase symmetrical amps that the breaker will interrupt. Now let's go over what that means. Circuit breaker interrupting capacity, or fault MVA, no matter what they want to call it, is usually listed in MVA. and we get it. It's a three-phase value, and it's usually listed in MVA because I think we mentioned earlier most faults are, say, from line to ground where you don't have hardly any resistance in the circuit. It's primarily an inductive circuit. So the value that is of most significance to us is the total amount of current and the voltage. So if we have the interrupting capacity would be equal to the, first of all, you got to remember the square root of 3 times the line voltage times the amount of amperes that the breaker will interrupt. Some of the terms I used previously was three-phase symmetrical RMS amperes. Three-phase we understand. RMS we discussed at our initial session, in that it isn't the peak value of an AC current, it's the root mean squared. That is the effective value of the AC current, the heating value, whatever you want to call this particular amperes. It's called symmetrical amps because of a set of conditions that exist on certain types of faults, primarily near generating stations. And it can best be explained by saying that when we have a particular type of fault, this means that the current in the generators of that particular generating station must instantaneously change to a much higher value. And since they have inductance in them, they can't do this. But yet they've got the requirement. So for a very short period of time, a DC current flows with the AC current imposed upon the top of that. So this means that we have a DC current starting out at some value here and decaying very rapidly within a few cycles, probably decaying in 5 cycles at the most. But on top of that, we have the AC fault current. So this means that we have a value of current here that is higher than the actual AC current. Now this is what's called an asymmetrical current. This is the way the circuit breakers used to be rated. But determining this value of the DC current, determining just how to apply this breaker proved to be too much of a problem for everybody. And so they decided the best way to get out of this was to rate circuit breakers in symmetrical amperes. This is a value that everybody knows the breaker can do. It can handle this particular current, and depending upon where the customer applies it in his own system, he can see if there is any DC transient, and if so, he can evaluate the effect on a particular circuit breaker and determine what size he'd want to buy. Another specified value is the operating time of the circuit breaker in cycles. As you know, from the moment a trip coil is energized, a protective relay operates till the moment that the contacts are parted, the arcing has completed, takes a certain amount of time. And this is called the breaker interrupting time. And circuit breakers, we have values now that start out about 2 cycles for 345 kV circuit breakers, and some of the faster AC, or some of the faster 15 kV circuit breakers that go up to about 8 cycles for 69, some of the older 69 kV breakers. We don't have any, I won't say we don't have any, but we have very, very few circuit breakers that are anything slower than 8 cycles on our system. Now these are the major requirements for a circuit breaker. Now depending upon the particular location that you want to install the circuit breaker, we have some additional operating mechanism requirements. At the particular substation, we may not have a large capacity 125 volt DC battery. Therefore, we have to have a pneumatic operating mechanism or a hydraulic operating mechanism. We have certain requirements as far as current transformers are concerned. We have to have a certain ratio. We have to have a certain number. Sometimes, as you know, in certain situations, we may want 2 current transformers on a particular side. Use one on a differential scheme and one on another relaying scheme. We have certain construction details that may be unique to our particular situation. We may want the control compartment raised a little bit because of a flood level. We have to have a particular type of terminal connector for the breaker terminals. And then writing these specifications, we also ask the manufacturer to supply any other particular information that he feels to be necessary to evaluate a bid on a particular circuit breaker. Now let's look at some of our applications of circuit breakers. We haven't really discussed too much low voltage, that is 120 volt or 240 volt or 480 volt circuit breakers, but yet we use a lot of them. The same principles that we've described up to now would apply for them. Their primary means of arc interruption is lengthening the arc by contact, by cooling it. The interrupting medium is usually air. We use a lot of them as control circuit breakers and lighting circuits and power circuits. We use a lot of 4 kV and 13 kV draw circuit breakers in our unit subs and our 13.8 kV switchgear. We use vacuum reclosers. As I mentioned, the one installation we have right now is at sub 73 near Cavanaugh, and we're considering vacuum reclosure for several other locations. 69 kV breakers, the breakers that we're using now, some of the latest breakers that we're using are the single tank breakers that we had the slides of, and it shows the development of the art of circuit breakers in that the smaller single tank 69 kV breakers have a capacity over twice as large as any of the 69 kV 3 tank breakers that was shown on the slide. The 3 tank breakers have a interrupting capacity of 1500 MVA. 1500 MVA. And the 69 kV breakers, single tank breakers, are rated at 3500 MVA. The 161 kV, we go up quite rapidly in interrupting capacity. The ones we're buying now range from 10,000 to 15,000 MVA. With continuous ratings of 1600 to 2000 amps. At 69 kV, let me backtrack a minute. At 2 or 3 of our locations now, we're buying 5,000 MVA circuit breakers. And the 345 kV breakers are 25,000 MVA. So before we get into our next section on breaker installation, do we have any questions that somebody may have thought of during the discussion, or some particular area that we might want to go into a little bit more? Mike?
Does the cost go along with this double rating?
Yeah, the question Mike asked, what does the cost of the breakers compare? We have a session that we're going to get into later, and I think maybe instead of doing it later, now might be the correct time to look into the cost of some of these circuit breakers themselves. Now, the 15 kV draw-out breakers, the breaker alone, without some of the cell, the switchgear cell that it belongs in, is in the order of $3,500 to $4,600. This is not a figure that would compare with some of the other costs I'm going to put up here, because this is the breaker alone, and it's going to be mounted in a switchgear cell, and the total cost would vary quite a bit. But breaker alone on a 15 kV draw would be something like this. Now at the 69 kV, the 3500 MVA single tank breaker, the breakers that we're buying now are in the order of $10,000. It's interesting to note that the 1500 MVA 69 kV type G04 circuit breaker that we purchased during the late 40s and early 50s at a price tag of from $15,000 to $18,000. So you can see breaker price and the product itself is the price is going down, the product is going up over the past years. And so really the manufacturers are doing some research. They're improving the product quite a bit. The 161 kV breaker price here is in the order of $40,000. This can vary a little bit below that to maybe $3,000 or $4,000 above that, depending upon how many circuit breakers you buy at one time and what the market price is. And then to go up to our 345 kV, 25,000 MVA breaker, that's $150,000. So you can see the price goes up rapidly as we go up in voltage and interrupting capacity. And this is just the price of the breaker alone. It doesn't include the installation, it doesn't include all the protective equipment that's necessary to control this circuit breaker. We have some 15 kV single tank circuit breakers. Not a whole lot, because most of our 15 kV circuit breakers are in switchgear. But we do have a few 15 kV oil circuit breakers that are single tank breakers. We have one out at sub 59. The 15 kV breakers on our mobile subs are single tank circuit breakers. But those are the two places where we have single tank breakers. I think some utilities that have a 115 kV voltage level can use a single tank breaker, but at the present stage of the game, that's about as high as they go in a single tank breaker. Well, now that we've got this circuit breaker, now we discussed what a circuit breaker is, let's see how our company used it and how we would install it. First of all, we have to select a particular breaker that we're going to put in one location. So to do this, we have to know the maximum fault capability or duty, let's call it maximum fault duty at that particular location. And our system planning people have board studies. Well, let me retract that. Board studies is not a word that's used anymore. They're called digital fault studies, that they can determine what the maximum current might be if we'd have a three-phase or line-to-ground fault at a particular location. Now, once we have that value, we can't say that's the value in 1969, therefore we should buy a circuit breaker of this capacity. We have to allow for future system growth. Now, we do that in a couple different ways. In some locations, we can look into the future enough so that we can say in 10 years we may have a maximum fault duty of so many MVA. So therefore, rather than put in one size breaker now and change it 10 years from now, we can buy a breaker now for the maximum fault that might occur in 10 years. Second method is to buy a circuit breaker that would meet our requirements for a shorter period of time, 2 to 3 years. And then as the interrupting duty increased, we'd move that circuit breaker, that location, to another location. This is a method that we've used quite often in the past because it saves us additional investment in circuit breakers. It postpones it. It means we don't have to spend that much money right now. And Chris, you're probably familiar with some of these 69 kV G04B circuit breakers that started out in the late 40s or early 50s at Riverside Generating Station. The fault duty increased there, and they moved from there to substations like 18 and S and R, and the fault duty is increasing at those substations. So they're being moved from those substations to other subs like 36 and 38 and Coralville and Fort Dodge, where the fault duty is much lower. So here's a circuit breaker that was 20 years old, but still is valuable in performing a function. It'll do its job very well, and at a much reduced cost over buying a new circuit breaker, because we've had this circuit breaker for 20 years, and even though it cost more to begin with, it certainly has a lot of depreciation in 20 years. Second factor in the breaker selection is what the continuous current rating of that circuit breaker would be. And this is going to be determined by the size of the transformer or overhead conductor that's on this particular circuit breaker. If we have a given size transformer, we don't want to purchase a 69 kV breaker or 15 kV breaker that wouldn't allow us to get the complete capacity of that transformer. So as far as transformers, all our transformers are being installed such that there is no component in the current carrying path that doesn't allow us to at least carry 125% of the maximum rating of that transformer. Well, as far as an overhead conductor, it means that we don't have any, or we try not to have any circuit breaker that wouldn't allow us to have the full current capacity of that particular overhead conductor. So this means that, for instance, if we have a 795 MCM conductor, ACSR, which has a current rating of 900 amps, we try not to install a 600 amp circuit breaker. We try to install a 1200 amp circuit breaker. Now, there are several places where we have installed 600 amp breakers on a temporary basis. That'll last for a shorter period of time, or because of the particular location, even though we have a larger conductor size, as we see it now, this section of line won't carry more than 600 amps. So these are the factors that determine the continuous current rating of the circuit breaker. Next, we get into after we purchased this particular type of circuit breaker, we get drawings from the manufacturer that give us some of the physical information on the circuit breaker. And so we get into the foundation design. Foundation design must have certain mechanical requirements. It must be designed for the weight of the circuit breaker, plus the impact of the opening mechanism. As you remember from some of our sketches, in opening the circuit breaker, we drive the contacts down. This is an impact force that must be added to the actual weight of the breaker to use in designing a foundation. And then we also have surprising enough, have an uplift force on the breaker when we're closing the contacts. We're inherently performing a closing operation that's going to tend to lift the circuit breaker. These factors have to be considered in design. One thing we're very conscious of right now is the flood protection of a circuit breaker. We don't install any equipment, if at all possible, where the control compartment is not above the 200-year flood level in a particular location. Sometimes what we have to do, if we are establishing a given elevation for a foundation, it might mean that we may have to put in a little steel pedestal there, or an I-beam, something that's going to lift the breaker and the control compartment as much as, I think we've gone as high as 10 to 12 inches just to get the control compartment above the 200-year flood level, because this means that that circuit breaker would still operate even though some other parts of the breaker might be underwater. If we had water level up to here, the breaker, as long as the operating mechanism is out of water, is still going to be operable. We have to allow for ease of maintenance of the circuit breaker, so that we put a pretty good slab underneath the circuit breaker. In the maintenance procedure, the steel tank of the circuit breaker is lowered so that the electricians can inspect the contacts, they can clean them off if necessary, they can adjust the contacts so that they close at the same point in all three phases. And so one help to doing that is to have a concrete slab here, so when they lower the tank they'll have something to sit on. And we tend to extend the slab out beyond the control compartment. So during the inspection, the weekly inspection of these circuit breakers, when somebody's standing there, he won't be standing in the snow or rain, or, well, there's nothing to do about the rain, but you can try to keep his feet from getting too wet. In the circuit, or in the foundation design, we also have to consider the connection to the control compartment. So this means that we're going to have a controlled duct run coming up through the foundation. You might want to look at a few slides on that later. Now these are some of the factors they have to consider in the foundation design. In installing this circuit breaker in a given structure, obviously you have to have clearance of any energized part to ground, so that you're not going to be installing a safety hazard. To help maintain these circuit breakers, we always put a disconnect switch on either side of the 69 kV circuit breaker, a 161 kV circuit breaker, or a 345 kV circuit breaker, or some type of isolating means on both sides. In some cases where we have a bus with a circuit breaker connected and then a transformer immediately connected to that breaker, we sometimes omit a disconnect switch here and then rely on the secondary circuit breaker of the transformer. Because when you have any one of these breakers open for maintenance, well, the transformer is completely dead anyway. We also must consider in our circuit breaker and also our structure design clearance to move the circuit breaker in and out. This means that in our structure design we have to be sure that we're not putting bracing on all sides of a bay that we have a circuit breaker in, because this might mean that it would be kind of awkward to try to get that out at a future date. The connections to the terminals of the breaker should be sized to meet the continuous current rating of the breaker. They also should be supported in some manner so that they don't provide any mechanical stress on the bushings of the transformer, either by using a flexible conductor that's supported from above it, or if a particular substation design requires tubing, it means that you have to have a flexible connector at the bushing to allow this tubing to expand and contract. The operating mechanisms of the particular circuit breaker mean that we have to provide a 125 or 250 volt battery. In the case of a solenoid breaker, it means that we have to provide a 240 volt source to an air compressor or a hydraulic pump that builds up the accumulator pressure. It also means that the wire that we run from a power source to the circuit breaker has to be of sufficient capacity that during operation it doesn't drop the voltage down enough so that the air compressor or the solenoid won't operate. This is quite a factor in a solenoid operated circuit breaker, because the closing current there we're talking about 190 to 200 amps. The control conduit connections from the pad or from a duct run to the control compartment are being installed with flexible conduits. So if we have any relative movement between the duct run and the breaker, we don't pull the bottom out of the control compartment. We might want to look at a few of these slides again, and perhaps we can go over some of these installation details. And if you have any questions, well, don't hesitate to answer. This particular view here shows some of the factors as far as structure design. In this case, we have isolation from the breaker terminals to the steel structure on either side. We have a flexible copper conductor that will be attached to a bushing here that allow for expansion. It's also a sufficient capacity to carry the breaker rating. And as you can see in this location here, we have space that we can move the circuit breaker in and out. This little pad here is the pad for the operating mechanism here to allow easy access to the operating mechanism. This particular view here, it shows that we have to have a pretty heavily reinforced foundation for the different forces that exist in a circuit breaker. As I recall, 161 kV circuit breaker, 10,000 MVA is in the order of, what figures have we been using, Tom? 140,000 pounds? Or is that the total, including the uplift?
40,000 pounds.
Is it 40,000?
60, yeah, I think 63,000.
63,000 pounds. That would be the weight of 161 kV 3-tank circuit breaker.
What would be the other forces you're talking about, the impact you're adding to this?
Usually it's about the weight of the circuit breaker. So you're talking about a total force of
120?
2 times or 2.5 times the weight of the circuit breaker.
161. And uplift would be once the weight, 63,000 pounds of uplift. It would just equal out, because there wouldn't be any weight. No. It would lift the weight itself up. Plus a 63,000 pound force. I see. Any overturning?
No, I think the only forces that we're talking about in the circuit breaker design are vertical forces. Now this view here gives some of the other factors we want to consider. Another thing that we haven't mentioned up to this time, but it's very important in circuit breakers, is to make sure that the circuit breaker is grounded. We can see here we have a ground conductor here that's connected to the substation ground grid that grounds the tank, and we have another one over here. This particular area here, you can just see an area here where we have a controlled duct run coming up into this junction box here, and then from this junction box we go into the control compartment of the transformer. And this area here was poured initially. We have an expansion joint all the way around this, so you could have differential settlement between the circuit breaker control riser there and the rest of the foundation. This view here, we see the grounding of the substation tank there. We see some steel conduit coming up here. It's our later practice to use flexible conduit in this location right here. And up here we have the terminal connectors for the breaker bushings that we have to specify, and the current from here up to the isolating disconnect switches.
When you say flexible, what do you mean there?
The flexible steel conduit encased in plastic. Seal tight is a conventional trade name for that.
Steel or case or something?
Yeah, it's a flexible steel conduit that's composed of a series of interlocking steel rings, basically is what it is. And then the overall conduit is encased in plastic to make it weatherproof. Jim, did you have?
Yes, on the unit shows prior to this, the control box had 2 insulators on it, plus 3 pumps. This control box, no, yes, the control box there appears to have 2 insulators on the top.
Question is about the 2 insulators.
Right.
I think that's from a circuit breaker that's behind this breaker. Yeah, this. Some of these pictures don't show everything that we could, but they, all in all, they're very good pictures. They're taken by our official photographer. No. As I say, some of these show earlier installation practices. Now, do we have any more questions about 69 kV or any kind of circuit breakers? Denny?
Is there some sort of a device, a counter or something that measures the number of operations? And
Yes.
is the circuit breaker overhauled or something after a certain number of operations?
To answer the question, first of all, is there an operation counter in the circuit breaker? And the answer is yes. I don't know if we can see it in this, some of these views here, but there is an operation counter for in the mechanism. Let's see. Well, I guess the answer to the question is yes. There's some device there that I think may be the operation counter, but there is an operation counter to record the operation of the circuit breaker. Our present practice is to maintain the circuit breakers on a given time period rather than after a certain number of operations. And I think on circuit breakers we've gone to a 4-year maintenance period. And one reason for this is that it coincides with the maintenance period of other equipment in a given substation, as for instance the transformer. And it means that the substation division can move a crew in and maintain all the equipment on this particular substation and then move on to another one instead of maintaining a certain type of equipment, as for instance a circuit breaker, and then moving on to another substation. It's our practice to maintain everything in a substation that has the same maintenance period at the same time. Some type of equipment they maintain at shorter intervals. Transformers and circuit breakers, I believe, are on a 4-year maintenance period. Relays and meters, I think, on a yearly maintenance period.
Reclosing and recycling times.
Reclosing, the question is, what is the reclosing time?
Yeah, well, I don't know, maybe that's not important, but how long, for instance, recycling on these spring ones, does it take a while before it could go back to the surface?
Yes, the question is raised on a reclosing operation. Any type of circuit breaker can be reclosed. Some are more designed for it because they have a faster closing mechanism. And these are primarily the pneumatic circuit breakers, in which we can open the circuit breaker and reclose it in, say, 20 cycles. So that means the circuit would open, and you get a closing impulse and it close in 20 cycles. Now, on pneumatic mechanisms, depending upon the control, they could do this 5 times. We don't have any 69 kV or 161 or 345 circuit breakers that reclose more than once. On 13 kV circuit breakers, we have a reclosing relay that allows them to reclose 3 times before a lockout. That is, if they have a fault, they would close 3 times and trip 4 times. And these are spaced between the different periods, not so much on the capabilities of the operating mechanism, but just to allow any type of fault that might be on the circuit to clear before they're closed in again. The solenoid mechanism has a much slower closing mechanism, though it isn't quite as adaptable at 69 kV to be closing. The spring-operated motor, I believe, requires about 19 cycles to charge up the motor. So this would mean you can always trip once and reclose once. But then once you've tripped open again, it would require 19 cycles to charge up this closing spring before you could close it again. Now, did that answer the question, Chuck? Jim?
What's the advantage of the pneumatic and hydraulic operating systems compared to the solenoid type?
Question is, what's the advantage of the pneumatic and hydraulic operating mechanism over the solenoid mechanism? First of all, you get a faster closing operation. With a solenoid type of circuit breaker or operating mechanism, because of the inductance in the coil, it takes time for this current to build up and close the circuit breaker. So a typical closing speed might be 20 cycles. It takes quite a while for a solenoid operating mechanism to close a heavy operating mechanism that's on a 69 kV breaker. So the pneumatic and hydraulic mechanism just have more muscle to close the breaker faster. And this is the reason they're doing it on any type of reclosing operation where you have to open and close again. It can store a certain number of operations at the breaker. You have 5 stored operations in any type of pneumatic or hydraulic operating mechanism. And it also means that you don't have to have a large 125 volt DC battery. To operate your solenoid mechanism, you have to have basically 200 amperes, which is quite a lot of amperes at DC. It means you have to have a pretty good sized battery. However, for a pneumatic or a hydraulic mechanism, where you're only using the AC or DC for control purposes only, you're picking up a little relay that the only current requirements you may have may be 8 or 10 amps. So for all these reasons, manufacturers have kind of gotten out of the solenoid operating mechanism, except in the 4 and 15 kV draw-out mechanism. And even at those levels, they're tending to eliminate them in favor of either the spring wound or the spring operated mechanism or some type of a hydraulic mechanism. Well, if we have no further questions, that's all for tonight.